We've talked about work and energy for quite a while now, but it's time to answer the big question. Why did we introduce these concepts? Because as we will see, this will help us look at the world in a completely different way. So let's take an example. Imagine you take a bowling ball in your hand and let's say you throw it. What's going to happen? Well, that ball will speed up as it leaves your hand. Now, if we ask the question, why did the ball speed up? What is the answer? Well, we can say, well, when you were throwing that ball, you were pushing on it, so you put a force on it. And whenever you put a force on any object, that object accelerates, and therefore it speeds up, and that's why the ball became faster. And this is in accordance to Newton's second law, which says F equals ma, which means force will accelerate a body. Of course, if there are more than one forces, then we have to calculate the net force, but we'll talk about that later. Let's consider only one force as of now. So you're putting a force and that accelerates the body. That's one way to think about it. Now let's think in terms of work done. You see, because you are pushing on it and you're displacing that body, you're doing work on that ball, right? And when you're doing work, look at what happened to the ball. Initially, it had no speed, it was at rest, so it had no kinetic energy. But then after doing work, notice it has gained kinetic energy. So we can now say that by doing work, we have added kinetic energy to our bowling ball. And so by doing work, whenever work is done on an object, kinetic energy gets added to that object. This is the new way of looking at the same situation. Now you can also do work and remove kinetic energy if you want. For example, imagine a ball is thrown at you and you try to catch it. Now when you try to catch a ball like this, again, your hand will move back a little bit. Now think about what happened. When you try to catch that ball, your hand will start pushing it, but this time it pushes it in the opposite direction. And that's why it's slowing it down, right? But now think about the work done. Because you're pushing it in the opposite direction to the displacement, work done is negative. And now when you're doing negative work, look at what happened to the kinetic energy. The kinetic energy reduced. So we can now say when you do negative work, you are removing the kinetic energy from the body. So negative work removes kinetic energy from the body. And this is, crudely speaking, what we call the work-energy theorem. It basically says when you do work, you either add or remove the kinetic energy from the body. If you don't do work at all, then the kinetic energy will not change. Of course, we'll derive the mathematical version a little bit later, but before we do that, let's look at some more examples. Let's say now you take that bowling ball and you drop it from some height. Now as it falls down, it's going to speed up. Again, let's look at work. In this case, in this particular case, gravity is pushing down on that ball and the ball is moving in that same direction. So gravity is doing positive work. And because gravity is doing positive work, it's adding kinetic energy to that ball, and that's why the ball is speeding up. Similarly, if you were to take that same ball now and throw it up, let's say you threw that ball up. Now, as that ball goes up, you might know it slows down. Again, what's going on? Well, again, gravity is pushing down on that ball. Remember, gravity always puts a force downwards, but this time the ball is going in the opposite direction. So gravity is doing negative work. And as a result, gravity is removing kinetic energy, and that's why the ball is slowing down. This is pretty cool, right? Thinking in terms of work and energy. Now, things get even more interesting when there are more than one forces acting on the body. So if there are more than one forces acting, according to Newton's second law, we need to now calculate the net force, meaning we have to add up all those forces. Well, of course, if the forces are in the same direction, we add them. If they're in the opposite direction, we subtract them. But anyways, you calculate what the total force on that ball is, and that will tell you what will be the acceleration of our body, right? Now, similarly, if there are more than one forces acting on the body, you calculate the total work done by all the forces, and now that decides what happens to the kinetic energy. So if that total work done by all the forces becomes positive, kinetic energy will be increased. Kinetic energy gets added. If that total work done ends up becoming negative, that means kinetic energy will be removed. And if the total work done is 0, which is totally possible, some forces can do positive work, others might do negative work, and we'll look at some example. Then the total work done can be 0. In that case, kinetic energy will not change at all. Again, let's look at a couple of examples of that. Let's say there's a cupboard on a very rough floor, very heavy cupboard, and you want to move it. So you start pushing on it. Let's say as you push on it, you slowly displace it from here to here. Now after displacing, after you've pushed it, the cupboard is still at rest. So let's think about the kinetic energy. Initially the kinetic energy was 0, it was at rest. After pushing also, the kinetic energy is 0. So the kinetic energy didn't change at all. So it was neither added nor removed. That means the total work done on this cupboard was 0. Why? Clearly you pushed on it, you did work. Then why is the work done 0? That's because there are more than one forces acting over here. So you are pushing on it and you are doing positive work. But because the floor is rough, friction is pushing on that cupboard in the opposite direction, doing negative work. So you are doing positive work, friction is doing negative work. So it just so happens that the two work dones cancel out. Total work done ends up becoming 0. And that's why the kinetic energy didn't change at all. Another way I like to think about this is when you're doing positive work, I like to think that you are adding kinetic energy to the cupboard, but at the same time, friction is removing that kinetic energy from the cupboard. And that's why the kinetic energy didn't change at all. Okay, let's do one more. Say I take this very cute puppy, which is initially at rest. It's at rest right now. I push on it and I raise it up slowly. And finally, again, it's at rest. So even here, the kinetic energy did not change. That means the total work done on this puppy is 0. But why? Clearly, I am pushing on it and I'm making it move. So why is the total work done 0? Can you pause the video and think about this one? Well, again, I am pushing on it and I am doing positive work and I am trying to add kinetic energy to this puppy. But there's one more force acting on this puppy. Which one? Gravity. Gravity is pushing down on that puppy. And as a result, it's doing negative work because it's in the opposite direction of the displacement. And so gravity is removing kinetic energy from the puppy at the same time. So I'm trying to add kinetic energy, gravity is removing the kinetic energy. And that's why there is no change in the kinetic energy at all. So my positive work is canceled out by gravity's negative work, making the total work done 0. So now that we have some idea of the work energy theorem, let's go ahead and derive the mathematical equation for it. This will be useful for problem solving. All right, so I need to connect work and kinetic energy, right? So again, let's start with just one force. If there's one force acting on the body, then the work done by that force, the work done would be the force multiplied by the displacement. Let's call the displacement as S. Okay, what do I do next? Well, I want to somehow bring velocities into the picture because I want kinetic energy, right? And I can do that by substituting F equals ma, because that's how acceleration comes. And then from acceleration, I can bring velocities. So if I substitute F equals ma, so I'll get m times a times s. But I don't want acceleration. I don't want displacement. I want velocities. So can you think of a connection between acceleration, displacement, and velocities, initial velocity and final velocity? Yeah, go back to equations of motion. Think about this. Great idea to pause the video and see if you can remember an equation. Well, there's an equation, v squared equals u squared plus 2as. This is perfect because this will help us connect as and write it in terms of v and u. So I want to get rid of as, isn't it? So let me isolate this on one side and put everything else on the other. So if I rearrange this, we'll get v squared minus u squared divided by 2. That equals a times s, right? So now I can substitute that over here. So that'll give me m times as is v squared minus u squared divided by 2. Oops, let's use the same color. U squared divided by 2. And now if I open up that bracket, see what I end up with. Left-hand side is work, and that equals mv squared by 2. What is mv squared by 2? That's the kinetic energy, final kinetic energy. So we can call it as the final kinetic energy, minus, you get mu squared by 2. What is mu squared by 2? That will be the kinetic energy initially, before I started pushing it. And this is the work energy theorem mathematically. It's saying the same thing that we discussed already. If you do positive work, notice the final kinetic energy will be more than initial. That means you're adding kinetic energy. If you do negative work, you are removing kinetic energy. This equation is also telling that if you do 100 joules of work, as an example, then your kinetic energy will increase by 100 joules. So you will add 100 joules of kinetic energy. Similarly, if you do 100 joules of negative work, then you will remove 100 joules of kinetic energy. So you can kind of now see what work really represents. When you do work on a body, what happens to that body? Its kinetic energy changes. So whatever work you do, that much kinetic energy gets added or removed. And again, if there are more than one forces acting on the body, what happens? Now you just have to calculate the work done by all the forces. So we can say this will be the total work done, or we can say this is the net work done. So the total work done on a body will decide how much kinetic energy gets added or removed. And we will see in future videos that certain kinds of problems can be solved much faster by using this equation rather than F equals ma. Okay, so to summarize, what did we learn in this video? We learned the work energy theorem, which is basically saying that when you do positive work on a body, you add that much kinetic energy to the body. And if you do negative work on that body, you remove that much kinetic energy from the body. Of course, if there are more than one forces acting on the body, then you have to calculate the total work done, and that decides how much kinetic energy gets added or removed.